Hello and welcome back. And we are now in the last module. We're in the home stretch. Um, I know that technically Monday is a holiday coming up. It's Memorial Day, so happy early Memorial Day. But we still have two chapters worth of stuff. And considering, the format asynchronous, we can get through these last two chapters in 2 weeks. I have um, obviously decided not to go with an extra homework assignment for this chapter, although I thought about trying to do something fun with it, and I thought, no, you know what? Let's just go through the chapter, this chapter, and then we'll have a quiz on it next week. We'll go through chapter 14, which is behavioral disorders, next week, which is the last week. And a reminder that because there's no class technically on Monday, that the last portion of this would technically be Monday, June 1st, and that evening is when your um, final paper and the extra credit are due. I know that I was planning on giving instructions on how to write the final paper. I don't remember if I actually posted a little video of that or not, so if not, I'll do one later today. But let's get through the last two chapters. Learning and memory is, of course, one of my favorites because it talks about how the brain learns things and how it retains information and all of the fun biological functions that are happening. I will split this up into two lectures, and we will go from there. So, even though there is technically no class on Monday, and I have not decided if I'm having office hours or not, probably not, but I do have my 92 class that has a paper due that day, so I might just decide to do it. But either way, I will open the quiz for you guys on Monday, the 25th, should you want to take it on the holiday, but obviously you have till Friday, so there's no worries about that. This looks a little hectic, but basically, we open up with what we know about learning and memory really comes from a lot of what we know, most of what we know really comes from one person. And this person, whose name is Henry Molaison, is a guy that we were able to study his brain. Well, not me personally, but we were able to study his brain because he had very bad epileptic seizures in the early 1950s. As a teenager, he got into an accident on his bike. It caused a head injury, and helmets were pretty sparse back then. So his life was very much affected by these seizures. They were so bad he would lose control of his bodily functions, and there is a video here for you to see. If you had me for Psych 1, then obviously you've already seen the video because I talk about it in the memory chapter there. But his epileptic seizure treatments at the time was an experimental surgery. This was when neurosurgery was fairly new and not common. And so the doctor that looked at the activity in his brain decided to take out an area in the middle, kind of behind on the inside of the temporal lobe. We talked about this pretty important structure of the limbic system called the hippocampus. And obviously we have a left and a right temporal lobe, and he took out both hippocampi, as you can see from the diagrams below. So what happened to HM after he had his hippocampi removed is the seizures stopped, and he seemed to be living a relatively normal life, except for one little problem. He couldn't remember anything new or make any new memories after the surgery. So he had what we call anterograde amnesia, which is the inability to form new memories. If he were to have retrograde amnesia, and maybe sometimes you guys have seen, maybe I think it was one of the Muppet movies where Kermit hit his head and couldn't remember who he was or things from before the injury, that's what we would call retrograde amnesia. HM also had some retrograde amnesia. He did lose a few memories from the decade before he had surgery, but most of his childhood memories and things like that were secure. Um, when we talk about this form of amnesia, it is imperative to point out that there are two types that we'll get to of memory. One is memory for dates and events, as you see here on the slide, um, names, dates, events, memories that you've had, which we call declarative memory. So when the hippocampus was removed for HM, he had no new ability to make declarative memories. But there are a few other, or at least one or two other types of memory called non-declarative memory. So if you recall from Psych 1, whether you had me or not, if you recall from Psych 1, Ivan Pavlov and then John Watson ran with this idea called classical conditioning. And the biggest thing, just to review, of classical conditioning was your brain automatically makes an association between two things. So if you hear a loud noise like a balloon pop, your automatic reaction is to flinch and get scared. With Pavlov and his dog, the dog um, associated food with a bell that Pavlov rang. And so when they rang the bell, the dog started salivating as if food was coming. This type of memory is unconscious and is non-declarative, and it uses different parts of the brain than the hippocampus. So the other type of non-declarative memory, as we'll get to, is procedural memory, which is sort of memory for doing a task or doing a procedure. So if you get better at something by practicing, sometimes this is called muscle memory. So with muscle memory, you get better at hitting a baseball at 90 miles an hour. You get better at learning a dance move. You get better at cooking. You can declare that you got better, but the only way you can actually prove it is to show people. So non-declarative memories are classically conditioned memories and procedural memories of doing a thing like artwork, signing your name, right? Muscle memory sort of tasks. And those do not involve the hippocampus. So even HM, with his loss of declarative memories, he was still able to get better at a mirror tracing task that you'll see, or maybe you watched it before this. And even though he didn't remember ever doing the assignment, he got better at it. He also got better at a task called the Tower of Hanoi, and I have included that video for you as well. So you can see, I actually used to give the Tower of Hanoi to Alzheimer's patients when I would test them in my master's program. So when we're looking at learning, learning is basically the acquisition of new habits and new ideas and new things into your brain. Obviously, we're missing a picture here, so I'm going to go back to the, again, the slides that I give the online Psych 2 class. But we have basically three different forms of learning. It used to be short-term and long-term memory used to be the old way of thinking about things. We store things in the hippocampus for short-term memory, which is also called working memory. And I'll get to that in a second, and long-term memory. So it used to be that short-term memory was a few seconds to a few minutes, and then long-term memory was anything after that. But nowadays, we think of it as short-term memory being, again, a few seconds to a few minutes, long-term memory maybe a few seconds to a few days, and then long-lasting memory being potentially for the rest of your life. So if you'll allow me, I realize I have to go back a little bit because I didn't realize that this slide was missing. But if you just allow me, we can go to the top here. I can choose a slide. So at least I have this default setting for this. It's my crappy computer that's the reason for that. So if you look here, and obviously I will zoom in, you can see that the consolidation of memory is basically in nowadays it's thought of in three stages. So short-term memory is something that lasts a few seconds to a few hours. The old definition of short-term memory was trying to keep things in your brain as long as you could until you either remembered them long enough or were able to write them down. So in the days before cell phones, or let's just say, if you want to make it a more modern type of example, let's say you left your cell phone at home, not like we're leaving home very much these days, but let's just say that you did. You ran into someone, you wanted their number for purposes of a job or an opportunity, or you wanted to date them, whatever it is, right? You wanted to get their phone number and you didn't have anything to write it down with. And of course, you didn't have your phone to put it in. So the old version of short-term memory was this idea of taking 7 or 10 digits, remembering them long enough to either write them down or to keep them long enough in your brain, a few seconds to a few hours, to be able to get home and then put it in your phone or write it down. Working memory is a newer term, which we'll get to a little later, that refers to the fact that it's probably a little more complicated than just learning a few words or a few letters or a few numbers to write down. And that we're constantly adding information, bringing stuff back from long-term memory to combine and all of that stuff. Long-term memory, again, used to be thought of as anything more than that, hours to the rest of your life. But now we think of long-term memory as something that may last hours to months if you never recall it. After you learn it or things like that, it may disappear. So think about songs maybe that you learned and you used to listen to a lot 5 or 10 years ago, that you may remember some of the words now, but maybe not. And now the term for memories that last up to a lifetime, we neuroscientists now call long-lasting memory. So that's the slide we're looking at here. Going back, if we can hopefully get this going on, here we see that when the brain is trying to keep memories longer, that the difference between this short-term and sort of long-term and long-lasting memory is looking at the location of where the information is. When we are first encoding this information into our brain, it's that hippocampus that allows for short-term storage. So short-term memory, at least declarative memories, are stored here in the hippocampus. And you can see from this scan, this would be a PET scan, that there is activity in the hippocampus. One of the things in Psych 1 that I taught, and I don't know if every Psych 1 professor goes through the idea of sleep, but sleep causes what we call consolidation of memories. And consolidation is the term for moving a short-term memory that's been encoded temporarily in the hippocampus, moving it while you sleep into long-term memory to store it up in the cortex. And so during sleep, we know that we have dream states. We're not going to get into the sleep chapter here because we don't have time for that. I wish we did, but we don't, and I don't want to cram more in for you. And so we take those temporarily stored memories from the hippocampus, and while we're sleeping, during this stage called NREM2 or non-REM2 sleep, sometimes it happens during REM sleep a little bit, is these memories get stored and transferred up to the cortex and stored as long-term or long-lasting memories. We know that this is true because this scan is actually showing the hippocampus lighting up and moving information as we're sleeping. So if you ever wondered why sometimes dreams are often accounting for just what we did that day, if you spent a lot of time on Tumblr, if you were playing Tetris, right, and you dream about falling blocks of different shapes, it's because one of the strongest theories of sleep is that since we're consolidating memories, we are activating those circuits, and that's why a lot of what we dream comes from what we did that day. So this is the idea of consolidation. You're consolidating those short-term memories into long-term or hopefully long-lasting memories from the hippocampus up to the cortex. Now, again, this is Declarative memory is an active process. Non-declarative memories kind of automatically go up there, different parts of the brain as well. So during retrieval, one of the things that we have learned in neuroscience is that the neurotransmitter that guides learning, memory, and retrieval seems to be glutamate. Remember, glutamate is the main excitatory neurotransmitter, and I did talk about it early on, and probably I think it was chapter 2, that glutamate is involved in learning and memory. And we obviously can perform experiments to figure this out. If you block glutamate, you can see up here it says glutamate is required for consolidation and retrieval. And if you block glutamate receptors, it prevents both consolidation and retrieval. So if you block it before the person goes to sleep, you give them glutamate antagonists, what you're going to find is that those memories are not able to be recalled later on. So not only do they not get consolidated, but they don't get retrieved. If they're not consolidated, they never make it to long-term memory, so there's no way we can retrieve it. And also looking at fMRI scans and things like that, what we see is that when we are trying to retrieve memories, the prefrontal cortex, which helps us to make decisions, coordinate memories and things like that, is definitely leading the search. Sometimes, somebody may ask you a question and you know the answer and you can find it right away. My friend Gabe and I, he was my old roommate before Dr. C was born. And him and I obviously grew up and glorified 90s. We love 90s movies, 90s music, pop culture, trivia, all of that stuff. So although we have Google at our fingertips, sometimes he and I will text each other if we can't figure out the answer, just to see if the other person knows it, before we consult the almighty Google, just because it's more fun to see if we can come up with the answer before we look it up. And there'll be sometimes when he's like, do you remember the name of the band that was a one-hit wonder that had this song in like 1995? And right away I'll be like, oh, that was blah, blah, blah. Or sometimes I can't think of it, but I'll wait. Instead of trying to Google it, I'll wait, because sometimes it'll come to me 10 minutes later. Sometimes it'll come to me 3 hours later. Sometimes I'll forget about it and it may come back to me like a week later. And so there's no rhyme or reason for that. But sometimes, it's just not, the file's just not open, or it takes a lot longer to get there, right? But it's up there. And sometimes I just can't remember it all. So I say, okay, let's consult Google. Looking here, you can see that when people are perceiving things and when they are recalling things, we see similar scans, right? So on the left would be perceiving. So pictures are obviously perceived, as we have already learned in chapter 10, in the occipital lobe. So you can see right here that in the back of the brain, in the occipital lobes near V1 and the others, that's where the sounds are being perceived when they're pictures, when a person is first looking at it during an fMRI. For sounds, obviously we see the temporal lobe, the auditory cortex areas and Wernicke's area, to be able to interpret what the sound is. And when we are during recall, what we see is very similar activity in the same areas where the information was first perceived. Here in the left side, remember language is on the left side, so when we're perceiving, we see it coming in on the left side, not really as much activity on the right. But what this shows us is that people used to think from the 1960s till probably the 1980s, or at least, for a good portion of that time, that memories were stored in just singular specific spots. And maybe that somewhere in the frontal area was your memory for your ex, and somewhere in the middle was a memory for, playing baseball and stuff like that. They also used to believe back in the day that all of the memories you ever had were stored up there, just ready to be relived. If we look at the examples of popular influence of movies like Disney, Pixar's Inside Out, they would have you believe that the core memories are just these little balls that are stored and you can just recall them. Even movies like Eternal Sunshine of the Spotless Mind with Jim Carrey. He had a really bad breakup with a girlfriend. She went to a place that had a procedure that could just remove all memories of your ex, and she did it. So he went and did it, and then, well, you can see what happens if you really want to watch the movie. I'm not going to spoil anything for you, even though it's in that sense. But what we find, based on this picture and based on what we know in neuroscience, is that memories are stored all over the brain. Just like I told you guys, we use 100% of our brain and all of our neurons, not just 10%. The places where the association areas of these places, auditory cortex and temporal lobe, visual cortex and the occipital lobe, these are all where the memories seem to be stored. So for one given memory, let's just say that, picture and sound, let's just say that you're remembering the last time you went to Disneyland when it was still open. What you saw, you processed in the occipital lobe, and the memories of the visual evidence of what you saw are also in the occipital lobe. What you heard at Disneyland, the sounds that you heard, were processed in the temporal lobe and the auditory cortex, and memories of the sounds that you heard are also in association areas of that auditory cortex. So what we smell and taste are going to be, underneath the prefrontal cortex. What we touched or what touched us is going to be near the somatosensory cortex. And so memories are stored all over the brain in different areas, and memory, like language, seems to be a function of a circuit of different neurons. And really, when we're recalling something, all we really need to do Olvera Street in downtown, um, near the train station, and you smelled some churros. And all of a sudden, just the smell of those churros reminded you of the last time you went to Disneyland when you ate churros. So just the smell was able to activate that entire circuit and bring back that entire memory, which is stored in many areas around. You activated the circuit and the whole memory came up. So sorry, Jim Carrey, as much as I love you in your movies, um, it's science fiction because we don't have just specific memories specific neurons that we can destroy and boom, your ex goes away. Although some of you might wish that could be true. I don't know. So looking at the hippocampus and surrounding areas, one of the other things that we sort of talked about with the hippocampus in chapter 3 was that the hippocampus is also, in addition to being part of the limbic system, part of our emotional system, which also brings up memories, of course, is that our hippocampus is also the place for what we call our spatial GPS. Um, and what that means is that there are special cells within the hippocampus that basically kind of form a map of our environment. So, you may know some of these people that are really good at directions that don't really need GPS so much. If they go somewhere once, their brain sort of takes a mental picture or makes the mental map of how to get there. And I feel like I'm one of those people. When I was little, whenever my dad would drive around, as soon as I was old enough to sit in the front seat, I would sit in the front seat. So when we drove to Vegas or San Diego, to the Valley, wherever we went, we only really had to go to a place once. And then I pretty much, for the most part, knew how to get there, even before I could drive. And I feel like Dr. C inherited that from me. And so that's this area of the hippocampus that you're able to figure it out. I also know people who go the same way every day and they feel like they need their GPS just to make sure they don't get lost, even though they do this on a regular basis. As easy as going to a friend's house that they see once a month or something like that, and it's always the same house. But they feel like they need that GPS or they're going to get lost. which is okay. Some people have stronger spatial mapping skills in their hippocampus, and some don't. My story about Dr. C, really quick, if you guys will indulge me, and you kind of have to because I'm doing this solo, is that when he was maybe a year and a half old, um, we go to the hospital at Cedars-Sinai, which is right behind the Beverly Center. And my wife had an asthma attack, and it was about 8:30 at night. Carter was definitely in bed asleep, and I needed to take her to the ER to get a breathing treatment. And there was no time to find somebody to watch the kid and all of that. So I had to just obviously wake him up, take him with us, and then hang out with him in the waiting room while she got whatever treatment. So it was dark at this point, almost 9 o'clock at night when we got there, and we were driving down La Cienega, and then you turn onto San Vicente to go behind the mall to get to the emergency room. And I don't know if you guys took Psych 41 at all, or if you had the developmental chapter in Psych 1. I didn't teach that one. But when Piaget and these developmental psychologists talk about the fact that if there's a giant building or mall in the way, that children are not able to understand their stuff behind it. So this was, one night. And then about a month later, maybe 3 to 4 weeks later, we got, my wife and I get our glasses at a place in the Beverly Center. So during the day on a weekend, we told Carter, hey, we're going to go to this mall and get a new pair of glasses that we had ordered. And he said, okay, maybe, 18, 20 months old. So we drive down La Cienega before we even get to San Vicente. And Carter's like, ooh, where are we going? And I said, oh, we're going to get our glasses. And so we drive past San Vicente to go to the Beverly Center. And Carter goes, oh, is mommy okay? And I said, what do you mean? And he said, are we going to the emergency room? Are we going to Cedars? And I said, no, why? Why would you say that? And he's like, because this is the way we went to Cedars-Sinai. And I was like, but we're going to the mall right here. He goes, no, it's behind the mall. And apparently, children of that age, a year and a half old, are not really supposed to understand that, let alone the fact that it was like almost 4 weeks later that he did it when he was half asleep, and it was at night where it's hard to see. So that's when we were like, oh, looks like this boy's not going to have a problem with directions. So I feel like genetically I passed that down, hopefully. But the reason that I come up with this is because what was discovered in rats and in humans is that if you place a rat in a circular maze, every time the rat's head turns to a different direction in the maze, there are a cluster of cells in the hippocampus that fire. And the reason we know that is because they basically recorded all the cells in that part of the hippocampus in studies where rats were in a circular maze. And as you can see, every time the rat oriented its head towards a certain portion or part of this circular arena, a different color would come up. And the different colors would light up based on different clusters of neurons in that part of the hippocampus. So up in the top right area here, we see a lot of dark green. Here we see a lot of really dark blue. Here we see light blue. Here we see red, and here we see purple and black. And so whenever the rat turns a certain way, and I'll try and find a good video on this if I can on YouTube, every time the rat turns a certain way, those specific cells would fire. So it tells the rat, I'm in the, southwest corner. I'm in the southeast corner. I'm south. I'm north. Without actually saying those things, so that it can tell where it is within its environment. And the firing increases when they are in a specific location. So maybe you'll get a little bit of green here, all right, a little tiny blip of green. But when you're in this, oriented towards this area, what we would call, I guess, northwest up here, right? North, if this was north, south, west, east. In the northwest quadrant, you get all of those cells firing a lot. If you're in the northeast quadrant, you get all of these light blue cells firing more. If you're due south, you get the purple ones, right? So it basically forms an entire map of your spatial environment. Oops, I didn't mean to do that. Let's go back. So it's dependent on environmental cues and landmarks. And we see that this is also found in humans. And why did it do that again? Humans and primates. In mice, I was actually able to run a test called the Morris water maze, which I will show you, that allows us to see if mice can learn based on, this is environmental cues and landmarks. So if you've ever heard people say, right, GPS and stuff will say, make a left on Cesar Chavez, make a right on Atlantic, right? You may have seen or you may have heard in the past that people sometimes use landmarks. Go down to that street. Well, I don't know what that street is. Oh, well, on the corner there, there's a McDonald's. So when you get to the McDonald's, turn left. And when you get to the Rite Aid about 4 blocks down, then you turn right. So taking these environmental cues and landmarks and say, go to the donut shop and turn left, go to the McDonald's and turn right, go to the, you know, whatever it is, and then you'll get to ELAC. I actually ran this water maze where I had a circular, right? I had a circular pool with water, and just under the surface of the water is a little clear platform. And mice are innate swimmers, so they can swim. They don't need to learn. They're born knowing how to swim. They just don't necessarily want to. It's sort of a survival skill. So their motivation in the pool is to find a way to not have to swim. So under the surface, and I usually put it in the northwest corner, I put a little platform about a centimeter or so under the water, and then I put some non-toxic paint in the water to make the water white and milky. So you couldn't just see the platform. You had to basically swim around and find it. And so what I would do is I would have them swim 4 trials a day over 6 days, so 24 trials. And outside of the pool, I would put, there was like a plus sign and a triangle and another picture here and another picture here on the walls. So they couldn't see me. I would duck down. I would duck down underneath. And they would just be looking at the landmarks. And I would drop them in different areas. I would drop them in southeast, southwest, northeast, and northwest would be where the platform was. So I would never drop them in right here. And I would see, did their times get faster? I would give them up to 60 seconds to find the platform, and then I would take them out if they didn't. And I'd place them on the platform for 60 seconds so they could look around and see where they were. And to show learning, what they did was, you know, their times got faster, their path that they took, the amount of that they swam got shorter and shorter as they learned where the platform was. And, you know, what used to take 60 seconds is now down to like 10 seconds by the end. And this shows that they were able to use spatial cues and understand where they were and be able to locate the platform by using this spatial map, using these place cells. I did this in, as we talked about glutamate, I did this in mice that were, that had no deficiencies, which we called wild type, and I used a special mouse model that had one gene missing that was believed to be involved in schizophrenia in a lower capacity. And what the gene does is it lowers your glutamate levels. So glutamate function is interrupted. And what I found was that by day 6, these mice caught up to the wild type regular mice, but they had a lot more trouble in the first beginning trials trying to figure out where the platform was because they just couldn't learn as efficiently. So we talked about memory and consolidation and all of that needing glutamate. Well, learning also needs glutamate. So they were able to catch up eventually, but it did take a little bit longer. So again, HM, going back to the idea of HM, he, despite his impairments and the fact that he couldn't remember even eating multiple meals in a row because he couldn't remember, he was able to still improve on non-declarative memories. He was still able to get, you know, classically conditioned associations, and he was still able to improve on a mirror drawing task, as well as what the video didn't show was the Tower of Hanoi problem. And again, I will add that for you guys. So since you can't see it, we're going to go back over here, and I am going to go back to the right page. And of course, the next thing you get is that you have all of these extra pages at your disposal to take a look at. Oops. I think memory as a function of the hippocampus. Let's check here. I believe it is. Come on. And yes, here's the place cells. And by the way, this is a illustration of the water maze. So here you can see at the very beginning over here that the mouse is trying to find this platform under the water, and it swims all around and does all these crazy turns and twists, and finally eventually finds it. After learning, we finally find that you drop the mouse off here. The mouse sees that there's the proper, stuff over here, and goes whoop, and directly goes there. So the path, we call that the pathway, or the amount of swimming, how many centimeters or whatever that the mouse swims, gets shorter and shorter, and they find it after 5 seconds instead of 40 seconds. So that's the Morris water maze. Here is the Tower of Hanoi problem. So basically what's going on here is that you have two rules. You have to take this tower of discs and you have to make it onto one of these other pegs. But the trick to it is that you can not take any of these discs and just put it down on the side. These discs have to go on one of the other pegs on the next move, and the only real big rule is that you cannot put a bigger disc on top of a smaller disc. So you can't take this one and put it here and then take this one and put it on top, right? You'd have to take the small one and put it here, and the next size one maybe put it here, and then take the smaller one and put it back on top. And maybe you can visualize this, or you can watch the video of it. HM was not very good at this at first and never remembered taking the test, but over time, like the mirror drawing task, he was able to solve it in less moves and able to get better at the task. So that's what this is. Going back, again, we have, and we have another missing picture, but we can see that the hippocampus is involved in declarative memory, and those are things like memories of emotional events and things like that. The non-declarative memories actually involve two structures, the basal ganglia and the cerebellum. So obviously you can see how those motor centers, as we learned from chapter 11, will play a role in muscle memory, or non-declarative, what we call procedural memory. So riding a bike, signing your name, doing things that are muscle memory, getting better at this tower task, getting better at this mirror tracing task. Connected to the hippocampus is actually involved in both processes. It is basically when emotions are tied to memories, the amygdala is also involved. So if you recall something that makes you emotional, that would be declarative. In non-declarative, if there's some sort of unexpected thing. So one of the examples I gave a few minutes ago with non-declarative memory would be popping a balloon and causing a scared, startled sensation. In non-declarative, the amygdala would be playing a role in that unexpected emotional response while performing a behavior, or if you hear, what could be a gunshot or just a loud balloon pop or something like that, and cause your emotional system to go into overdrive. The amygdala is playing a role there. In declarative memories, when you're remembering grandma, and grandma may no longer be with us, and it makes you emotional, the amygdala in this declarative memory is also being activated. And remember that in the limbic system and directly, the hippocampus and the amygdala are active and connected to one another in both directions. So I also did in my dissertation a thing called fear conditioning. And in fear conditioning, you put mice in a box and you play a tone for about 10 seconds. And at the end, the last half second of the tone, you give them a little foot shock. Now, again, it sounds bad, but it's just kind of like getting a static electric shock, right? Rubbing your feet on the carpet and then touching somebody or touching something metal in Vegas. So it doesn't really hurt. It's not long lasting, no tissue damage, but it's enough to make them learn. So the whole process of learning to associate the tone with the shock is the um, amygdala. But knowing the environment that you're in, if I put them back the next day in the same box, they may freeze right away just because they're in the same environment. And knowing the same environment, the spatial awareness, is the hippocampus that's connected to the amygdala. So again, my apologies for the my apologies for the oh, I guess that's the next one. For the lack of slide. Let's see. I probably don't even have it in here. So here is, oh yes, here we go. We skipped one. My bad. So again, declarative memory requires the hippocampus. Non-declarative memory requires the striatum, which is 2/3 of the basal ganglia. That is the minus the globus pallidus. So it is the we'll just go back here because it's just easier. My apologies. Um, the hippocampus is declarative memory. The cerebellum and the striatum, or 2/3 of the basal ganglia, right? The putamen and the caudate nucleus. So here we see, if I may zoom in a little bit, we see a person with a rat at the end of these arms of this thing that's called a radial arm maze. And again, I will give you a little bit of insight on the radial arm maze. Looking at the different parts of the brain, we are able to lesion or basically damage, destroy a part of the brain in these animals to find out what they can and can't do in the presence and absence um, of those brain structures. So we know that declarative memory from HM requires the hippocampus because HM's hippocampi were both of them were removed from the left and right hemispheres, and he could no longer remember anything new. When we lesion a rat hippocampus in this maze, basically what you do is you put the rat in the middle of the maze here, and there are 8 or so arms that the rat can go down to try to find food. So let's just say there was food here at the end, and this was the one that's south compared to the researcher that's in the north area. When you lesion the hippocampus, normally a rat would remember which arms it went down to get food. So the next time you put the rat in the maze, if it's just fine, it will go back down the arms in which it had already had the food. When you lesion the hippocampus, that declarative memory of where it had been goes away. So rats will keep revisiting the same arms of the maze because we could tell that they had no memory of which ones they visited. For non-declarative memory, again, that requires the striatum. And that's, again, when I talked about fear conditioning and things like that, is associating the tone with the fear. Or if there's a light that goes off that tells the rat, okay, now you can go down here to get food. When you lesion the striatum and not the hippocampus, they won't go down the same arms because they'll have the memory for the arms they visited, but they won't be able to get that classically conditioned association of when the light turns on, now you go. The light meant nothing to them, or a sound in fear conditioning would mean nothing to them when this part of the brain is lesioned, when it's destroyed selectively. So we can see that declarative memory requires the hippocampus. Non-declarative memory does not require the hippocampus, or HM would not have gotten better at the mirror drawing or tower test. Non-declarative memory requires the striatum, most of 2/3 of the basal ganglia, and also not pictured here, it requires a cerebellum, but that's more for coordinating the, balance and things like that. So let's see if we can go back and get some things from the actual slideshow that I provided. Oh, look at that. We don't see much here, but there's actually a cool, and hopefully you get this when you download these yourself. There is a really cool, oh, I guess this is it. So really cool idea when we talked about working memory. So one of the things that I went over a little bit earlier was that originally we used to think of the temporary storage in the hippocampus for these declarative memories as what we called short-term memory. In short-term memory, you just think of a few letters, a few words, or a few numbers. Hold them and practice them and rehearse them, right? Somebody gives you their phone number, 8675309, 8675309, 8675309, and boom. Hopefully you remember it long enough to put it in your phone when you get home or write it down when you get to the car or something like that. With working memory, this is sort of an updated concept that memory researchers realize that we're not just dealing with a bunch of numbers or letters or words, and that this is a conscious, active process. We're not just taking a few things and holding them until we can write them down. In this way, we are taking pieces of information, we're maybe adding or subtracting to it or changing it. Sometimes we're even taking things that we learned that are already in long-term memory and we're sort of changing them for a little bit. So working memory is defined as sort of a temporary register for information, and that it just shows that it's not taking a bunch of things and holding on to them, but that we're actively processing new things. So one of the biggest examples from my childhood in the 80s and 90s was a game that we called Simon. And Simon was a game, and you can, by the way, find this at Target, I think, in the as a retro game for all of us old people to remember. But basically, Simon was a round disc that you put batteries in, and it had 4 buttons that lit up a different color, red, green, yellow, and blue. And each of those buttons had a distinct tone, one higher or lower than the next. And it was a game of memory. So you would have to learn the pattern. And if you got it right, starting with just one sound and one color, then you would go on and improve and go to 2. And if you got that right, you'd go to 3. So you'd hear boop, and it was maybe the color blue. And you'd hit the blue button, and it would match the sound. Boop. So you had the sound and the color. And then it would go boop, boop, up, blue, green. Boop, boop. Oh, you got that right. Now you go to 3. Boop, boop, boop. Red, green, yellow, right? And so on and so on. And you would try to, each time that you got it right, you would add another one to it. So not only do you have to remember the pattern that happened before, but now you have to add another one to it. And this is the same thing in your generation, most of you. In your generation these days, that toy that sort of replaced or upgraded from Simon is called Bop It. And in Bop It, you had things that you pull or twist or push or kick or whatever, hit, lick. And every time you get the pattern right, you add another one to it. So you have to keep a memory of the entire pattern you just learned, and then you add another one to it. And then you have to remember that pattern and add one to it, and blah, blah, blah. In psychology testing, we have what's called the delayed non-match to sample test. So basically, in this case, you have to remember a pattern for a short period of time. Maybe there's a delay period and you don't see anything, or maybe we even distract you with something. And then we show you 3 new shapes and we say, pick the new shape. So this involves not just the hippocampus, but connections with the prefrontal cortex. Remember, that's directing our search strategy and trying to keep things in and maybe bringing back long-term memories, right? So as you can see on the left, the prefrontal cortex is able to integrate long-term memory with other new information from the hippocampus. It also manages strategies and decision making and helps to direct this active learning, working memory traffic in the brain, where we are constantly updating and changing information. So it coordinates our sensory and motor systems, it coordinates our memories and all of that. So the delayed non-match or the delayed match to sample, you're looking at three shapes. Here we have a square, a diamond, and something else. Then we have a delay period where we see nothing. And when it comes back, we have to figure out which shape was not there. Obviously, the square was there, and the stop sign looking thing maybe. But the Pac-Man was not there. That was a diamond before. So you have to be able to recognize what it is, and you have to be able to recognize what it's not, right? So you have to know what the other one was replaced with. And this requires what we call working memory. So you can see how this is sort of an upgrade from the idea of just learning a few digits or a few letters or words, right? So that's the newer idea. Sorry, I keep getting emails. Biology. A lot of times we talk about things that can't be directly studied, right? There's a lot of these things that we call constructs. With constructs, we see things like intelligence, right? Intelligence, we know that people can be smarter or less smart in this case. But the only way that we really can measure that is indirectly. You can't measure intelligence by doing a brain scan. Sometimes you can see thicker and more connections, but that's not really leading to intelligence necessarily. Intelligence, we give an IQ test and you get some sort of number that's associated with it. Is that an actual direct measure of intelligence? No. What about emotions? We can see emotions running higher or lower. We can see parts of the brain that light up with these emotions, but can you actually directly measure emotion? The answer is no. Some of these things are called constructs, and we can indirectly measure them. We can look at things like in aggression, like blood pressure, right? Before somebody is upset and angry and after, and we can see physiological changes like increase in blood pressure. But again, you can't directly measure that. For the brain, for learning and memory, it was a long time believed that this was also a construct. It was also believed that every single thing that you ever learned and that you would have a memory for, and it was just ready to be relived, you just needed to open the right file, so to speak. We realize now that that's not the case, but we were able to figure out actual physical proof of learning and memory in the brain. When we are sending information from neuron to neuron and structure to structure, obviously in chapter 2, we learned about the firing of neurotransmitters across the synapse and picked up by the receptors. And so a regular working synapse, if we think about it like as an equation, we'll call that a 1.0. So the idea behind learning something is that you're potentially strengthening the synapse between them, which requires stronger and more neurotransmitters, as well as a response from the postsynaptic side. So one of the things that in the late 60s, early 70s, that, or should I say late 70s, early 80s, that researchers were working on is the fact that we know that electrical activity can artificially stimulate the neurons, right? So in action potential, you have to have enough sodium to depolarize the cell and reach the threshold. This we've already established. But if you were to put an electrode into that cell, zap it and give it some electrical activity that depolarizes the cell for you, then it will automatically fire, right? Makes sense. We can artificially make cells fire by giving them voltage, by giving them, right, depolarizing that cell. So researchers wanted to know If they were to give a train of stimulation, 100 hertz each, 100 hertz each time would be enough to cause an action potential. Researchers said, what if we gave 100 stimulations in a row? What if we just caused it to go up by 100? Just bam, 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 and give 100 pulses of stimulation that would cause a huge increase in action potentials. There's no question that it would increase the activity of the cells. The question that they had was, would it come right back down, or would that activity stay increased for a long period of time? And so they said, well, let's try it. So they gave 100 stimulations of 100 hertz volts of electricity in a row to a cell. In this case, they used the sea slug called the Aplysia, California sea slug, because although the sea slug is a tiny creature, in comparison to humans, the axons of the nervous system in the Aplysia are actually quite large. So they were able to easily put an electrode in there and give stimulation, 100 trains of stimulation. They stimulated serotonin cells that release serotonin. And what they found was, again, before the regular firing of a cell, we'll call it a 1.0 here, they gave it 100 trains of stimulation and increased it 100-fold. And it increased the function and it increased the firing and receiving of the cell. And even 25 minutes later, it stayed increased. So if you think of this as doubling the activity, we went from a 1.0 of activity to a 2.0. So what that means is the synapse became stronger and stayed stronger over time. And this was believed to be, as they artificially did this, the neural basis of learning and memory, or the physical proof of learning and memory in the brain. There was a man who, way before this ever happened, named Donald Hebb. He said that when two neurons fire together, that the synapse between them strengthens, and he called this, they called this the Hebb rule. Basically, he said two neurons that fire together wire together. So if you are learning associations between two things, right, and we can use the idea of classical conditioning and Pavlov and the dog for this, right? Here is a regular, right, 1.0. This is like the bell ringing. When you pair the bell with the food, bell, food, bell, food, bell, food, you get this increase in response. When you pair up a weaker synapse with a stronger synapse, the synapse becomes stronger over time by association. So this is something called, this is something called LTP, long-term potentiation, and this is believed to be the physical proof of learning and memory in the brain. When you learn something new, you strengthen the connection of those neurons, and it stays strong, and you go from a 1.0 before to a 2.0 after. That's physical proof of learning. You get more neurotransmitter, and to make up for that on the other side, because again, we have receptors that only take up so much neurotransmitter. If you were to not do anything on the postsynaptic side and just release a whole bunch more neurotransmitter, it wouldn't pick any more up. You'd just be wasting neurotransmitter. But in order to go to a 2.0, you'd have to have the postsynaptic side also make changes and maybe bring up more receptors to take up more neurotransmitter. I realize this probably sounds very foreign, and it sounds like a lot, but we will go through this. In addition to LTP, can we reverse it? So obviously, if you give a low train or a very small amount of electricity, what you're doing is blocking and preventing action potentials. Action potentials come when you depolarize enough. If you were to give 1 hertz stimulation, which basically blocks it from being able to depolarize because you're giving it such a low amount of electricity, we see electrical activity, we see exactly the opposite. You go from a 2.0 down to a 1.0 or even lower. This has been known in reverse as LTP it says. This is LTD, long-term depression. So what you're doing is basically changing the cell so it goes from firing a lot, 2.0, down to 1.0 or less. And in this case, it reverses what LTP did. And this is believed to be when people forget or when they learn new ways to do things and the old way kind of gets lost. They believe that that's what's happening here is LTD. You're ditching the old thing for the new thing, or maybe you forgot something, and so that circuit kind of goes back down to normal or even below normal. So again, looking at it with the Hebb rule, this is what we call associative LTP using the properties of classical conditioning. Here on the left, we have a weak stimulation. So this weak synapse is the bell. When Pavlov first rang the bell, maybe the dog looked around because, dogs want to know what that sound is, but the bell didn't really mean anything. It's a very weak 1.0 synapse. The strong synapse here is the bell and, is the food that causes the salivation. So here's the food and here's the response, which is to drool or salivate. If we start to pair the bell with the food, pair the weak synapse with the strong synapse, eventually it's going to associate. And eventually after, maybe 20 times of bell food, bell food, bell food, by that 21st time, all you got to do is ring the bell, and now this synapse is just as strong, so the dog will salivate or drool just as much as if you actually presented the food, because in the dog's brain, when these neurons fire together, it wired together. So the dog eventually learns the bell means food is coming. So the response will be strong whether you give actual food or whether you just ring the bell, where the dog's brain knows that means food is coming. You're going to get just as strong a response, which is the response, of course, is salivating or drooling. So again, bell by itself means hardly anything. When you pair bell food, bell food, bell food, food causes a strong response in drooling or salivation. When you pair bell food, bell food, bell food, eventually just ringing the bell will get just as strong a response. So your brain has learned that two things, right, two connections mean the same thing. So neurons that fire together, wire together. And now you have a strong circuit. You've gone from a 1.0, paired it with something strong, and now it's a 2.0. Hopefully that makes sense. So the weak synapse is strengthened through induction, through pairing it with something that's already strong. So when we learn something new, we are strengthening the synapses in our brain. We are going from a 1.0 to a 2.0. Proof that we've learned is we can recall it. If we can recall it, if we get better at doing something like the tower task, right, then we are able to use that, and we are able to strengthen that. We are able to learn that and recall it. So of course, in this case, in LTP versus LTD, the rate of stimulation matters. High frequency stimulation, which will allow for more action potentials artificially, will elicit LTP. If we block that by using low frequency stimulation of 1 hertz, we are blocking the ability of the cell to fire an action potential, and we are causing LTD. So this is believed to be the neural basis. This was artificially stimulated, but believed to be how this works. In LTP, this is where we believe that this activity is increasing the strength of the cells by forming and recalling memories. We're learning new things, we're consolidating them, we're recalling those memories. You guys are learning these things so that you can take your final exam. Associative LTP, of course, is the idea behind classical conditioning. You pair a loud noise pop with the startling sensation, and it's going to do that every time. You pair the bell with the food, bell food, bell food, bell food. Eventually, just ringing the bell is going to cause the dog to salivate or drool just as if the food was coming. But what about LTD? Well, LTD seems to be weakening the synapse or bringing it back down to normal for either forgetting things that may not be important enough, deleting incorrect information when you have the real information there, or sometimes we don't want to saturate ourselves because we don't necessarily know what our capacity is, and maybe human memory, for most people, we need to make room for newer and better things. So it could be making space for new memories. But remember what Mr. Donald Hebb said, Cells that fire together wire together. So this is the idea of LTP. So how does this work? And I apologize that this is going to get a little specific, more than Psych 1 would. So remember in, I think it was chapter 5 that we talked about glutamate, maybe it was chapter 2, the end of chapter 2, where there are different receptors for the different neurotransmitters. GABA has GABA, but dopamine has like a D1 through D5. Acetylcholine has a nicotinic and a muscarinic receptor. And for glutamate, we have two different receptors. We have the AMPA receptor, which is basically ionotropic and just allows sodium channels to open and close really quickly. So when glutamate is released, and of course glutamate works really fast, a lot of times that's the AMPA receptors that are just opening sodium channels and allowing the next cell to depolarize enough for an action potential. But there is another kind of receptor that takes glutamate that's called the NMDA receptor. And although the NMDA receptor can eventually just cause sodium channels to open, the NMDA receptor is a special kind of receptor that is also metabotropic. So if you remember from chapter 2, ionotropic just opens and closes ion channels really fast. It's very fast acting, and boom, it's done really quickly. Metabotropic, we didn't get into all of the things that it does because it's not necessary to get into those itty bitty details, but the long-lasting, longer effects and cause other things to happen downstream. So it can cause protein transcription, it can eventually open things up, it can cause more things to activate enzymes and all of that stuff. So basically it just does a lot of work, and so it takes longer to enact, right? It takes longer to activate, but it also lasts a lot longer. So what we learned about ionotropic versus metabotropic, we can bring back to this. AMPA receptor, ionotropic, opens and closes sodium channels. Boom, boom, that's it. NMDA receptor eventually causes other things to happen downstream, which can include sodium channels opening. But the NMDA receptor is special because it's actually got something blocking that ion channel. So when glutamate binds to it, if only a little bit binds, there is a magnesium block on the NMDA receptor, as you can see here. And I can zoom in. That's, I think, no, maybe I can't in this slide. But here we see a magnesium block that is preventing these channels from opening. Much like when we talked about the action potential, it is voltage gated. So you need more glutamate, more depolarization to be able to knock that magnesium block off. So here, if an axon releases a little bit of glutamate, AMPA receptors are good. Open and close, sodium enters. If only a little bit of glutamate hits the NMDA receptor, nothing's really going to happen because that magnesium block is still there. But if we have more glutamate, or if we increase the amount, if it fires repeatedly, AMPA receptors are still working. NMDA receptors eventually knock off that glutamate, knock off the magnesium block, and the channel opens. So not only can sodium come through, but this is where the metabotropic part comes in. Calcium comes into the cell. Now, if you recall from the end of chapter 2, calcium is what causes changes to happen in the axon terminal. That's what causes the neurotransmitter to bind and to basically release. Now, on the postsynaptic cell, if you open calcium channels here, calcium can come in and cause other changes downstream, which lead to longer lasting changes, including bringing more AMPA receptors up. So it is the response to more glutamate. More glutamate is released during LTP. If it's enough to knock off that magnesium block, cause other things to happen inside the metabotropic version, right, the NMDA receptor, then longer lasting changes take place in this cell, including more AMPA receptors up to the top, more dendritic spines, and causes a reaction, because you can't have LTP unless you have activity on both sides. If you just had more glutamate release, it might not do anything else. we need more response from both presynaptic and postsynaptic cells. And I know this sounds a little confusing, and I apologize. So just as a look here, let's just say that here is this is by the way, what's it called? A micron spectrometer. So it's looking at the activity of a specific of dendrites activity. So in the red, this is the chemical or neurotransmitter. Here is a AMPA receptor that is coming off of a dendrite. So here, what we see is, we'll call this a 1.0. You have one little bit of neurotransmitter and one AMPA receptor to take up the neurotransmitter. When we have LTP, we're going from a 1.0 to a 2.0. So during LTP, more stimulation, more action potentials equals more, we'll just say it doubles the amount of neurotransmitter. So here's one glob of neurotransmitter, here's two globs of neurotransmitters. And in response to that, if we only had one receptor, then adding more neurotransmitter wouldn't really do anything. But through the power of those NMDA receptors, one of the structural changes, which includes increased number of dendrites. So here we see for a 1.0, one AMPA receptor was fine. For a 2.0, we have now doubled the amount of AMPA receptors. So we have double the amount of neurotransmitters, we have double the amount of receptors to take it up, and that takes us from a 1.0 to a 2.0. In strength. We've doubled the strength of the whole synapse, doubled the output, doubled the amount that the next cell can take up. So what are the structural changes in LTP? We see increased number of spines or receptors. We see enlargement of the dendrites. We see growth of dendritic spines and transport of additional AMPA receptors here. So we've gone from a 1.0 to a 2.0. So this is the physical proof of learning and memory in the brain. When you've learned that connection between bell and food for the dog, when you've learned something new in school, and you consolidate that information, you are strengthening the synapse. You are showing LTP, physical proof of learning and memory in the brain. So again, LTP shows more dendrites, more spines, more AMPA receptors that come up. So eventually you're going to see a little bit more volume in the hippocampus. And we have seen this in a study that was done in around the year 2000 with taxi drivers in London. I told you guys if we combine the information of place cells with this idea of hippocampus for learning new things, it would make sense that taxi drivers, this was before GPS was really even implemented full-time, that taxi drivers really needed to know all of the back streets, all of the alternate routes. They needed to have a really good spatial map of their environment, especially in London being a huge, huge city. And so what we saw in this, and I don't know if, I don't know if you can see this, but I'm going to go back here, and I don't think it's in here. Here's a radial arm maze, by the way. I got to go to the next thing, to the brain changes and learning, because we're on the next little portion. But here we go. But what you would be able to see is, and what you might infer from this study, is that the better that oops, that's not what I wanted. The better that a person has spatial for their environment, the more connections based on LTP, probably more volume in their hippocampus. So let's see, brain changes in learning changes in the brain. Let's see if it's in here. We're almost done with this portion. I'm going to go to the next one after this. But looking at the brain changes, again, if we were to zoom in here, I can show you guys that here's magnesium that's blocking the NMDA receptor. If you have enough voltage, more glutamate, more depolarization, then it's going to knock the magnesium block off, and we can get things to happen downstream when calcium enters. Um, so really quickly going back to, and here's oh, I guess there wasn't one. I thought there was a picture there for some reason, but I'm going to show you guys a video of long-term potentiation, and you can get all of these things if you go down to the other modules. But um, really quickly, that for the London taxi drivers, I guess there isn't um, a, a picture here, but they had those that just started driving, they had those that had only been driving for a couple years, and then they did brain scans of those that had been driving for 10 or more years. And what they found in this study is those that had the more experience that they had, the more, you know, developed their spatial map was, the thicker that area of the hippocampus was in brain scans. So more dendritic spines, thicker connections, and more more neuron density in that portion of the hippocampus. So the ones that had the most volume in that area. The ones that had been driving a little bit had less volume, but much more than the new drivers that just started. So you can see that with those changes in LTP, you get more spines and dendrites, thicker connections. You go from a 1.0 to a 2.0 or more. And the more experience you get, the more we can see the changes in brain scans. I think the last couple things, last couple slides for this are looking at the ideas of consolidation. In addition to glutamate for consolidation and retrieval of memory, we also see that there are enzymes that are involved. So when calcium comes into the cell, those glutamate, right, NMDA receptors, one of the things that calcium does is it activates an enzyme called CAMK2. And the CA in CAMK2 means that it's activated by calcium. That's what helps to establish LTP. Again, I'm not going to go into very minute details, but when calcium comes in, it activates CAMK2, and CAMK2 also helps to activate protein kinase M-zeta. So the only thing that you really need to know from this one is that it helps to establish long-term memories. It helps to cause more AMPA receptors to come up and increase the strength of the synapse to help with learning. The reason we know specifically that these enzymes are involved is if we took a mutant mouse we basically took out the gene that establishes CAMK2 or protein kinase M-zeta. What we see here in green, a normal mouse, this is that idea of fear conditioning, where you play a tone and then you give them a little shock, and the next day you play a tone and you see how much they freeze, because mouse, their initial main reaction to fear, right, something that's fearful, is for them to freeze like a deer in headlights. So those that were normal, that learned it on day one, they would still freeze 70 to 80% of the time, even after 50 days, just from hearing the tone and being in the same environment. If we were to use a mutant mouse that basically had no CAMK2 and no protein kinase M-zeta, they would, the first day, would still freeze about 50 to 60% of the time. By day 3, it's down to about 35% of the time. After a week and a half, they basically have no long-term memory of it, and so days 10 through 50, they're basically not freezing at all unless it's just a fluke, right? Unless they just stop moving for a few seconds and the computer picks it up as freezing. So what this shows is that those two enzymes, CAMK2 especially, and protein kinase M-zeta, are needed to establish LTP and long-term memory. And without them, the mice just seem to forget. So again, just to bring it back around, the idea of consolidation takes place during sleep, and what we see from fMRIs is when the person is learning new information, learning things that they see or that they hear, when they're trained, when they are sleeping during this NREM2 stage of sleep, when information is being processed and it's going from the hippocampus to the frontal lobe, you get the same pattern of firing as when they learned it. So as you see up here, neurons in the hippocampus and cortical areas repeat the same firing patterns that occurred when they were learning while being awake. So we know that there are genes during sleep that are activated that play roles in things like protein synthesis, modification of synapses, and being able to consolidate these memories from a temporary short-term storage in the hippocampus, declarative memories, to the storage in these association areas all throughout the brain. Again, what you see is going to be stored in the visual association areas. Things you heard from these memories um, are going to be stored in the temporal areas near the auditory cortex, and so on and so on. I guess the last thing that we're going to talk about, and really I probably should have broken this up at LTP, so my apologies, is memory modification. When we talk about learning, we talk about brain changes when we learn things, as well as LTD, which is brain changes when we are forgetting things or renewing things, right? So during extinction, we talked about in classical conditioning, pairing the bell and the food causes acquisition. If you repeatedly ring the bell and there is no longer a connection because there's no more food, then the brain goes back to this idea of extinction and saying, oh, that's not a thing anymore. So this could be, extinction could be learning that two things are no longer paired, or it could be a way to eliminate useless memories through either new learning, learning new ways to do things, and even extinction and memory modification for LTD requires activation of these NMDA receptors. So it's not just LTP, but it's also LTD that causes the NMDA receptor to make changes, maybe brings less AMPA receptors and goes back down to its original 1.0. This could be the case when we're forgetting old information, and does seem to be an adaptive active process. When we look at LTD and weakening of the synapse, we don't have, M zeta or CAMK2, but we do have an enzyme called PP1, which encourages memories to be lost. So maybe it's useless information or incorrect information, or it just may prevent the saturation of synapses. When we first recall a memory, we are actually prone to something called reconsolidation, and that can delete incorrect information itself. So if I say that I went to a party with Tony, Robert, and Seth, and I'm telling that story to somebody like my wife, and Seth is over at the house going, no, it wasn't Tony and Robert and me, it was Bart and Robert and me. I say, oh, I must have remembered it wrong. And then I reconsolidate it back into my memory. And if the information changes, that will change my whole memory. So our memories are not necessarily as rock solid as we'd like to think they are. I might tell that story over and over again for years, saying it was Bart instead of, Robert. And I would be completely wrong, but that is, again, an active process where my memory changed based on this different information. So this idea of reconsolidation is sort of an opportunity to refine memory and correct errors. We can actually use this technology of reconsolidation to try to help people with PTSD, post-traumatic stress disorder. So think about soldiers at war that are trying to not have to think about things that caused traumatic brain changes. So by using this idea of reconsolidation to try and lessen the impact of the traumatic experience, we can try to help them to sort of change the narrative on their trauma and try to make it more manageable and less harsh. It's also an opportunity for the brain to create memories that did not occur. So we can get misinformation by people changing it on us. We can also have false memories implanted. I actually had a situation at work where I told a story and a coworker of mine thought it was so funny and so amazing that he started telling the story as if it was him. And, I let him have it because that's his thing. But after a while, it occurred to me that after a month or two, that when he was telling the story, he actually believed it was him. And if he would have taken a lie detector test, he would have passed because he truly believed it was him in the memory because he had told it so many times. So our brains, our memory systems are not as rock solid as you'd like to believe. We can get misinformation, false memories. Sometimes people can think that something they dreamed was actually a real memory of theirs. And this may be beneficial to understand for people like witnesses of a crime or murder, right, that are put on the witness stand months, even years later. So we see these changes. We know that things are constantly evolving or devolving and things like that. So I'm going to stop here because this is way more than you actually need in one lecture, and I apologize for that. And I'll do a shorter lecture when we come back on the problems in learning and memory that are due to aging and things like that, some of the disorders that we come up with. So um, thanks for hanging out with me. I know it's been probably an hour and a half now, but we will continue this, and I will talk to you guys very soon.